gents, this is the moment you've waited for. You've been searching in the dark, your sweat soaking through the floor. And buried in your bones, there's an ache that you can't ignore. Taking your breath, stealing your mind, and all that was real is left behind. Don't fight it, it's coming for you, running at you. It's only this moment, don't care what comes after. Your fever dream, can't you see it getting closer? Just surrender, cause you feel the feeling taking over. It's fire, it's freedom, it's flooding open. It's a preacher in the pulpit and your blood devotion. There's something breaking at the brick of every wall, it's holding all that you know. So tell me, do you want to go? Where it's covered in all the colored lights, where the runaways are running the night. Impossible comes true, it's taking over you. We light it up, we won't come down, and the sun can't stop us now. Watching it come true, it's taking over you. Colossal we come, these renegades in the ring, where the lost get found, every crown of the circus king. Don't fight it, it's coming for you, running at you. It's only this moment, don't care what comes after. It's blinding, outshining anything that you know. Just surrender, cause you're coming and you want to go. Where it's covered in all the colored lights, where the runaways are running the night. Impossible close to intoxicating you. We light it up, we won't come down, and the sun can't stop us now. Watching it come true, it's taking over you. It's the 50 you ever want, it's the 50 you ever need, and it's here right in front of you. This is where you wanna be. It's the 50 you ever want, it's the 50 you ever need, and it's here right in front of you. This is where you wanna be. This is where you wanna be. Where it's covered in all the colored lights, where the runaways are running the night. Impossible comes true, it's taking over you. This is the greatest show. Greatest show. Impossible comes true, it's taking over you. Greatest show. We won't come down, can't stop us now. Watching it come true, it's taking over you. 'Cause everyone is right in front of you, and you see the impossible is coming true. And you can't stop us
Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
Hi everybody, welcome to Supercomputing 18. We love coming to supercomputing. In no place where all of us are working together to build the most important instrument of society, the most important instrument of science, and working together to advance humanity together. This is such incredible, incredible work, and we love doing it all with all of you. Thank you very much. I got a lot to talk to you about, so I'm going to get going. The topic of my talk is going to be the new HPC. The new HPC. How this industry is changing right in front of us and what it's going to look like someday. But before we start down that path, let's take a moment to acknowledge some of the achievements this year. It was 10 years ago that we, at this show, announced Tsubame 1.5, the first supercomputer in the world to be accelerated with CUDA. 2 years prior to that, we had introduced CUDA. It is now 10 years after that. Amazing achievements since. This year, we announced our partnership with Oak Ridge and IBM to build the world's fastest supercomputer. Ladies and gentlemen, the Summit. Incredible supercomputer. It just recently clocked in 144 petaflops of computing, 64 bits. It is the world's first supercomputer to also be powered by this new acceleration core we call Tensor Core that brings together multi-precision as well as deep learning. 3.3 exaflops of Tensor Core processing, all possible by 27,648 voltage GPUs. This year, 127 of the world's top 500 supercomputers are powered by NVIDIA. Ladies and gentlemen, that was Bob. He's very excited about it. 127 systems this year. The #1 fastest supercomputer in the world, the fastest supercomputer in America, the fastest supercomputer in Europe, and the fastest supercomputer in Japan, all powered by NVIDIA Volta V100. Thank you very, very much. None of that is possible without the energy efficiency of our GPUs. In fact, you can tell by the stats. 22 of the world's 25 most energy efficient computers are powered by NVIDIA accelerated GPUs. If you look at the trend chart, it's actually quite remarkable. Over the course of the last 10 years, early adopters and pioneers adopted our GPUs and continued to build larger and larger supercomputers with it. And over the last couple of years, it just kicked into turbocharge. And the reason for that is two things. There are two dynamics that are going on in the computer industry. It's affecting the entire computer industry, but it's affecting us here in supercomputing even more so. The two dynamics are the end of Moore's Law. It is no longer possible to build faster and faster computers at any ISO performance, ISO power, or ISO cost. We have to find another way to continue to extend computing because the application demand is there. Moore's Law gave us 100 times performance every 10 years, 10x every 5 years, 100x every 10 years. All of a sudden, it came into a screeching halt. Literally, in the course of 20 years, if we do nothing about it, we would be in a deficit of 10,000 times of necessary computing capability than what the market demands. We have to continue to find a solution so that we can continue to advance science. The solution, acceleration. Acceleration is not enough alone. We also have to bring all kinds of really special and very clever, innovative ideas to boost it even further. Those two ideas, acceleration and tensor cores. With tensor cores, we're able to bring to bear multi-precision that you'll see in just a second. Amazing progress using multi-precision, and secondarily, applying artificial intelligence, fusing it with first principle physics simulations to accelerate our discovery. Those two fundamental dynamics you'll see come up over and over again. But this year, we achieved a great result. I want to thank all of you, everybody in the ecosystem, all of our partners that made all of this possible. Thank you very much. The work that we do advances science. The work that we do advances humanity. And the amazing science that is being done each year is recognized by the Gordon Bell Award. recognizing those who are able to achieve extraordinary performance while applying it for discovery of new science. This year, there were 5 that were the finalists. 5 out of the 6 were powered by the Summit supercomputer, powered by NVIDIA's Volta. Some really amazing achievements. This is a weather simulator that trained a deep neural network from a highly precise simulation of weather to train a neural network to predict extreme weather conditions. And they achieved for the first time an exaflops of performance. Researchers at Berkeley Labs, Oak Ridge, NVIDIA. Researchers in Japan, in Oak Ridge, in the Swiss Computing Center at NVIDIA worked together on this seismic simulator of extraordinary scale. I can't wait to see the results of that. Simulating, recognizing earthquake impact and the damages to cities is a coupling of the seismic behavior as well as the structures that are on top of it and the structures that are near it. The coupling effect of seismic conditions affect the damages ultimately that we experience. They were able to achieve also extraordinary results. Using multi-precision and deep learning, the research team was able to achieve a 25x speed up in algorithm performance over what is currently used. Genomics, comparing a large variety of population genomic variations against known disease, they're able to better predict cardiovascular disease or Alzheimer's or even opioid addiction. The results here, I think, was 2.5, 2.3 exaflops. Extraordinary results. The fastest simulation the world has ever done. This one is using deep learning to detect the results from scanning electron microscopes of subatomic particles. And this is simulating quantum chromodynamics. Results are incredible. Again, researchers work together from all over the world, combining mixed precision, and in many cases, in 4 out of the 5 examples here, combining that with deep learning. The Volta Tensor Core, when we invented it and announced it at Summit, was welcomed incredibly. The researchers saw it and immediately jumped on top of it to take advantage of it and try to explore the limits. The researchers at Jack Dongarra's lab at University of Tennessee created a solver called Magma, which is an iterative refinement solver using our Tensor Core FP16 to emulate, essentially, FP64. And they were able to achieve results that were 4 times faster. So whereas FP64 is essential for science, its performance is limited. Always limited by energy and by performance, by bandwidth, by storage. Now with Tensor Core FP16, which processes FP16 at very high rates, we're able to use that particular method to achieve extraordinary breakthroughs. In addition to that, the earthquake simulation example that I showed you earlier was able to combine that with deep learning to accelerate their refinement methods. 23 times speed up. So as you can see, not only does acceleration bring enormous speed up, on top of that, we're bringing new innovations to speed up applications even further. I think that the next 2 major breakthroughs on top of acceleration are going to be the combining of multi-precision, mixed precision computing, iterative solvers, as well as deep learning and AI for preconditioning to advance and to accelerate the resolution of the refinement. Really, really exciting work. Well, the accelerating computing journey that we started a decade ago has really come a long ways. There's one thing that accelerated computing is not, and this is one of the topics I want to talk to you about, and what does it take to achieve accelerated computing? Because it's not just a chip. The chip and the architecture, of course, is the beginning. To create the right tools for the right jobs, recognizing that on the one hand, we want to continue to extend Moore's law and continue to, in fact, even accelerate Moore's law because there's so many pressing challenges that we can finally use computing to solve. On the other hand, Amdahl's law is always in front of us. If we can somehow accelerate 90% of the application infinitely fast, that last 10%, if slowed down, reduces the overall speed up that we can possibly get. And so recognizing that we use the best processors for the right parts of the code, accelerated computing instead of parallel computing, distributed parallel computing, we were able to achieve great results using the right processor for the right tools. The second thing, the right tools for the right jobs. The second thing that we did was recognizing that computing from first principles will continue to be essential. But there's this new emerging data science that we really ought to take advantage of. Fusing scientific simulation and data sciences, we could accelerate the discovery of problems that otherwise have no first principled equations. Maxwell's equation will work incredibly well when it applies. However, in the area of healthcare or life sciences, where the chemistry is so complicated, the biology is so complicated, there are no first principle equations that we can apply. There, we have to use data science to help us. Applying all kinds of techniques to further advance computation. Volta has the world's first tensor core processors. FP16 processing with FP32 accumulation. 8-bit integer processing with 32-bit integer processing accumulation. 8-bit integer processing with 32-bit integer accumulation. As a result, we could speed up applications into kernels that don't require the necessary precision, but yet as we accumulate and run the kernel for a long time, we have the necessary precision to be able to retain the overall accuracy of the application. One of the things that's really vital in accelerated computing is recognizing that it's really about the stack. There's nothing that's magical that hasn't been done in building CPUs. It's not like there's an extra cache that you could add, or extra bit, or extra mathematics operation that you can add to a CPU that all of a sudden binaries that were already compiled to will run so much faster. In order for us to achieve speed up these days, we have to design everything from the ground up for acceleration, but work with application developers in what the supercomputing industry calls co-development, to think about the entire stack, from the application to the solvers, to the libraries, to the architecture of the system, to the system architecture of the software, all the way down to the architecture of the interconnect and the chips. To think about the entire stack, that's how we're going to be able to overcome and, in fact, exceed Moore's law. And then lastly, any computing architecture has to be mindful of the single most important thing. The single most important investment and the single greatest investment that is placed on any computing architecture is developer investment and developer productivity. The body of work that sits on top of an architecture that lasts for a very, very long time is too valuable to throw away. And so we have to be mindful of that all the time, to be really thoughtful about productivity of developers, as well as making sure that the investment that is made is carried from generation to generation. This is one of the most important things about CUDA. If you take a look at CUDA, we're now on CUDA 10. CUDA 10 is our 7th generation GPU architecture with CUDA, starting with Tesla. Tesla, Fermi, many of you have enjoyed the architecture journey with us and have invested in the journey along with us. The Tesla architecture, the Fermi architecture, the Kepler architecture, which is still shipping in some supercomputers in the top 500, the Maxwell, Pascal, Volta, and then now Turing. Each and every single one of the generations advances new features. But it's vitally important that you recognize that we are disciplined to protect the old ones, so that the investments that were made in the past will be carried into the future. And the investments that were made in the past, the applications that were developed in the past, when the new processor comes along, we get even faster. So it makes the investment you made in your software last for a long period of time. And it makes the new investment you make in hardware instantly worthwhile. Forward compatibility, forward benefits, as well as backwards benefits. The discipline of a computing architecture is one of the greatest things that we've done. Accelerated computing is not an ISA. Remember, our accelerator is an I/O device, and this I/O device is virtualized, and its architecture is carried from generation to generation to generation. Look at the number of downloads of CUDA now. And these are running in data centers all over the world, as well as PCs all over the world. And so hundreds of millions of PCs and millions of processors and data centers all over the world now get the benefit of the increasing body of work. The thing about accelerated computing that is quite exciting is that as we continue to work with you on software improvements, the data center gets faster and faster and faster. If you take a look at this chart, what you're looking at here is Pascal and a Broadwell CPU, a server with 4 Pascals and 2 Broadwell CPUs. And nothing changes on the hardware configuration side. This is CUDA 8, CUBLAS 8, and CUDA FFT 8. And generation as the server is in operation, each and every few months, we continue to optimize the software. We continue to optimize the entire stack. And as you can see, we continue to improve its performance. The same exact piece of hardware, with optimizing the entire stack, along the entire stack, over the course of 2 years, went from a speed up of about 7 times to a speed up of 15 times. We literally doubled the throughput. We doubled the performance of your data center without changing anything, just the entire acceleration stack. And then when the new processor comes along, we add Volta to that, and bam, huge speed ups. This is the benefit of investing in an architecture. This is the benefit of optimizing the entire software stack, and this is the benefit of working together as a community to speed up the applications for researchers and scientists continuously, generation after generation. Well, it turns out, this is measured over an average, I think, of 10, 11 apps. It turns out we have plenty of work to do. This is what data centers look like today. This is the workload of a data center. This is the NERSC 20. This is what they're currently running in 2017, about 700 apps. 61% of the cycles are consumed by 15 applications. That's the good news. The good news is that if you accelerated 15% of the 15 applications, 61% of the workload, you've accelerated. So imagine if we took 50% of the workload, we improved its performance by 20x. By 20x, the overall throughput of the data center was boosted dramatically. However, there's a long, long tail, another few hundred applications to go accelerate. This is TAC. They have 1,000 applications, 80% of which is accelerated by 7 applications. This is NCSA, 200 applications, almost 70% represented by the top 10. And so the important thing to take away here is that it's a good news, bad news thing. The good news is accelerating 10, 15, 20%, 20 applications can really boost the performance of a data center. 50% of the time, 50% of the workload is now accelerated by a factor of 20. Another 50% needs to be accelerated. So the overall throughput of the data center is dramatically improved, probably by a factor of 10, but there's still an enormous amount of work to do. And that's one of the reasons why each and every single application we accelerate, we continue to maintain and continue to make sure that you benefit from it, because the next data center that you bring online, you're going to be running many of these applications. They've been around for decades. So important applications that we need to continue to advance. These are today's applications. So you can see almost all of them are based on physics simulations. Almost all of them. We're starting to see an emergence of machine learning being applied, data science being applied, otherwise known as data mining, being applied to discover new science. However, the vast majority of it is simulation-based. But we're seeing rapid changes, as I've shown you just now. So many new applications are starting to emerge that are multi-precision and that combine AI and physics simulations. The new HPC market's going to look like this. And I'm going to talk about how we're going to get there. The new HPC market, the old HPC market kind of looks like this. In 2010 or so, the world was undergoing some pretty dramatic changes that we're seeing today. And if you could just allow me a couple of seconds, I want to talk about some of the important parts of history that led us to today's computer industry that I believe will pave the way for tomorrow's. In 2010, the vast majority of high-performance computing was in supercomputing centers, higher ed, defense, seismic processing, data centers. But that represents the vast majority of the world's supercomputing centers, high-performance computing. Represents something along the lines of a $10 billion industry. The green is high-performance computing, physics simulations. The purple, represented by internet companies, the beginning of internet companies. A few companies that were using a very large distributed scale-out data center to do early versions of what is now known as machine learning. Then shortly after 2010, around the 2012 timeframe, three very important things happened. And they happened in open source. And now you're starting to see the benefits of it. But the three things that happen are this. The first is Pandas. Pandas is Wes McKinney's project, a library built on top of Python that allows data scientists to do data science work really, really easily. It's a Python library. And what enabled it is a work that was made possible by Travis Oliphant, who created NumPy and SciPy, that many of you in the audience surely know about. The basics of numerical libraries of today's high-performance computing, scientific computing, and data analytics. Pandas was essentially the Python version of MATLAB built on top of NumPy and was incredibly popular. It became, as you know, Python became the most popular language of data scientists, and Pandas is the most popular tool of data scientists. Meanwhile, there are people who are trying to solve the ETL problem, the data analytics problem, the machine learning problem, the iterative computing problem that Hadoop with MapReduce doesn't enable very well. And so Mate Zaharia at Berkeley created this project that ultimately became Spark. Spark is now used all over the world to scale out basically a data center and to turn a data center into one gigantic computer. A resilient, fault-tolerant, scaled-out data center numerical computing platform. The library was so effective, and it made it possible for data centers to become essentially one gigantic computer. Spark, used in tens of millions of processors around the world today. And then, of course, Caffe, the first framework that came along that helped us take advantage of deep learning, and was GPU-accelerated deep learning that people now remember as the beginning of the modern AI era, the big bang of that. All of that happened around 2012, somewhere between 2010, 2011, 2013, plus or minus. All of that was happening at that time. In the case of Caffe, deep learning proved to be incredibly effective, but it requires an enormous amount of data, and you need a lot of deep learning expertise, and you need a lot of deep learning infrastructure. It is still limited in the application all over the world. It is heavily used in internet companies that have an enormous amount of data. Spark is prevalent because machine learning has the benefit of domain experts being able to create their own features because of their understanding of their domain, and then to use those features that they design to train machine learning models using XGBoost or random forest or iterative random forest or k-mean or k-nearest for classification and regression. Almost every single internet company in the world that we know is founded based on that basic idea. And Pandas has turned everybody into a data scientist. Pandas is unquestionably one of the most important tools in modern science, whether it's sociology or forestry or oceanography or chemistry or biology or healthcare. Pandas is literally everywhere. Each has its own limitations. Deep learning has its limitations with understanding of the capabilities of deep learning, the amount of data intensity that is necessary. Spark requires an enormous data center. Pandas works in a really fantastic laptop, but it doesn't scale very well. So Pandas has scalability issues, Spark has difficulty to use issues, and Caffe has deep learning challenges. Each has its own issues. Well, a whole bunch of startups cropped up, and we worked with the ecosystem to figure out how to get us to the next level. In order to get us to the next level, there are several things we need to do. We need to find a way to apply the understandings of high-performance computing to scale up and to scale out machine learning. Scale up and to scale out machine learning. We know that machine learning requires in-memory computing, where the data is iterated upon, the algorithm's iterative. It is very compute intensive, it is very I/O intensive, it's very memory intensive, and it's not the type of computing model that works very well with simplistic scale-out approaches. We need scale-up computers. We need big computers. That's one of the reasons why Andrew Ng said deep learning is essentially like, machine learning is essentially like a high-performance computing problem. And I think a couple of years ago, he keynoted here and talked about that. And so our industry's challenge is to find a way to scale this up while protecting as much as possible the usability of some of the most important tools like Pandas. A couple things happened. If you take a look at what happened over the industry over that time, around 2014, a group of startups and NVIDIA worked together on GPU Open Data Science Analytics Initiative. We call it GoAI. And GoAI's goal was to solve some of the memory architecture challenges. There were so many different types of formats, and we know that if we're copying data from one memory to another memory, if we're copying data, we're not doing computing. And so moving data around is really an adverse to high performance. And so we worked together to find a way to unify some of the infrastructure of high-performance computing for machine learning. And so GoAI was started, built on top of CUDA, and what came out of it in working with Wes McKinney is this incredibly important initiative. It's open source. It's an in-memory data format. It's columnar. It's hyper-threaded. It's multi-threaded. And it is also zero memory copy, meaning that you can pass the results of one application into another application with an IPC without any memory copies, just by sending pointers. And that framework called Arrow is vitally important. Connectors coming in and out of it for all of the other sources of data. And now the world has one high-performance data format that it can build around. Meanwhile, the folks at Anacondas and some of the folks that are working on in open source around this area came up with Dask, which is a Python scalable library framework for numerics processing. Basically, Spark, but supports Arrow, built for Python, and is intended to be accelerated by GPUs. The formation of CUDA, Apache Arrow, and Dask led to the creation of one of our most important works that we announced recently called Rapids. Rapids is the world's first fully GPU accelerated data science pipeline from beginning to end. From the ingestion of data to the data processing, the joins, the filters, the group bys, to machine learning, XGBoost to random forest, k-mean and k-nearest, all of those entire workflow fully integrated on top of Arrow. And then with connectors, go take you directly right into PyTorch. And so you start out in machine learning, and before you know it, you're doing deep learning. And you start with machine learning because it takes less information, less data, and as you start to peak on your accuracy, you've also collected a large body of data through operating your model, then you can take that directly into deep learning. That entire framework, that entire journey from data analytics and data processing to creating engineering your features that are used for machine learning that are then taken into deep learning, that entire pipeline is now fully accelerated. We also, because we built it around Dask, we built it around Pandas, it's Pandas-like and it's scikit-learn-like. And so if you use scikit-learn, it's not possible to accelerate scikit-learn with GPUs, but we rebuilt scikit-learn, so it's scikit-learn-like. And so if you already have programs that calls these libraries, calling the new cuML library is super easy. If you've already written Python programs that call the Pandas libraries, your data science applications, porting that to cuDF, CUDA data frame, is super easy. And so we made it super easy to come onto this platform. And it's completely open sourced. We just released it to open source just a couple of weeks ago. This is just a fantastic piece of work, and I just really, really hope that all of you jump on it. Now, if you take a look at this journey, the amount of contributions from the open source industry that made this journey possible, if it wouldn't be possible without Hadoop, of course, and then all of a sudden Pandas and Python, inspired by Spark, and now we are building connectors to Spark. Spark has connectors into Arrow. Arrow is now a bridge into Rapids. If not for all of the contributions from Wes McKinney and Travis Oliphant and all of the people that are in open source working with us, just the hundreds of people in open source working with us to make this possible, this wouldn't be here today. I'm just so proud of everybody's work. Scikit-learn is an essential part of this journey. Pandas is an essential part of this journey. And so if you look at our framework today, it looks kind of like this. It's enabled by Dask, enabled by Apache Arrow. 2, that's a distributed computing math library, Dask scheduler. You have Apache Arrow, a high-performance, acceleratable data format that is columnar, hyper-threaded, and has the ability to communicate between applications using IPC, all built on top of CUDA, and then now Rapids on top of that, with interfaces that are essentially Pandas-like and scikit-learn-like, and if you use XGBoost, it just works. And so this framework, this accelerated framework, will help us address, as it turns out, the largest data science part of the market today. The vast majority of you who are using machine learning or doing data science are not using deep learning today. You're using machine learning today. It is much more accessible. It does the work that you need it to do, and now it's fully accelerated. Well, when we announced this, it's announced on open source. And the ecosystem that came out to support us and came out to include Rapids into their frameworks and their platforms was just extraordinary. In just literally 3 weeks' time, this is what happened. Almost everybody in open source who had contributed to this, from graph analytics to to libraries, numerical libraries, to all the startups that we worked with, did enterprise data science platforms such as Watson ML, and the Oracle platforms, the SAP platform, the SaaS platforms, and the cloud service providers, all of whom have machine learning labs and machine learning platforms in the cloud. We're integrating Rapids into them. And so now in the future, when you do machine learning, instead of waiting hours, instead of being limited by the size of data sets that you can use, instead of being intimidated by the type of machine learning that you're willing to train your models with, because it might take weeks, now it's completely GPU accelerated. So I want to thank all of our partners and everybody who has jumped on top of Rapids. This is really fantastic. I won't give you a data science demo because it either goes really, really slow or it goes super fast. But I'll show you some bar charts. Okay, so we, this is Wells Fargo's database. Basically, 16 years of all of the mortgages in America. And it's 400 megabytes of data or so. So this 400 megabytes of data, as you can imagine, will not fit in a graphics card. Our graphics card's largest memory is about 32 gig. On the other hand, it fits in system memory for a CPU server. Unfortunately, the CPU is too slow. So you have one of two choices. You have a circumstance where the memory is large, but the CPU is too slow, or you have this other challenge where the computing is fast, but the amount of memory is too small. And so this is the classic problem of scale out versus scale up. In the case of GPUs, we're trying to scale up computing. But scaling up computing, adding more compute, adding more bandwidth, comes at the expense of fast memories. On the other hand, you can get a lot of commodity memories, but it's at the expense of fast compute and plenty of bandwidth. And so these two challenges are being observed in computer science all the time. And that's why we have phrases like scale up and scale out. And in the case of scale out, we could do many jobs at the same time. In the case of scale up, we can do very few jobs that are gigantic. So scale up is used in data centers or supercomputing centers where there are few users, but they want thousands of nodes at one time. In the case of scale up, you have hyperscale data centers where they have hundreds of millions of users, but each one of them runs a job that lasts for a few hundred milliseconds. This world of data analytics, the world of deep learning, the world of machine learning, the world of data analytics is smack in the middle. It is smack in the middle. On the one hand, you want to have the ability, there are a lot of data scientists in the world. There are tens of millions. There are hundreds of thousands of deep learning engineers. There are tens of millions of data scientists. In fact, everybody who's graduating in school today will have to have a data science capability. And the reason for that is you can't do your work in forestry without data science. You can't do your work in biology without data science. And I think you might have seen it in Wall Street Journal that Berkeley's data science class is now the most popular class on campus. Everybody needs to be a data scientist. Whether you're in media entertainment, in marketing, in sales, in biology, in any field of science, everybody will be a data scientist. And so here you have a challenge where this is a very, very large market. There are going to be more data scientists than there are physicists. There are going to be more data scientists than there are astronomers. But every astronomer will be a data scientist, and every physicist will be a data scientist. The number of data scientists in the world is going to explode. And so we have this challenge now where the work that they do, the only way they could do their work is to process an enormous amount of data, to wrangle with that data, to play with that data, to try to figure out what insight they can discover from that data. And so here's an example of financial data, just mortgages data, just for the United States, several hundred megabytes of data. And ETL is called extract, transform, and load. Another way of saying you're going to get a whole bunch of data into your computer, and you have to find a way to slice and dice and filter it to create the training data set with your features engineered, the important features engineered, a training data set which looks about like a spreadsheet, except a several hundred gigabyte spreadsheet. This spreadsheet would then go into a machine learning algorithm to learn how to predict or how to regress, how to classify. And ETL, running on a Spark distributed server with 20 CPUs, takes something along the lines of 2 hours to wrangle the several hundred gigabytes of data. And it took several minutes on a computer we built that allows us to deal with big data. This is the single largest node that has ever been created. DGX-2 was designed to solve this very problem. This is the hallmark of scale up. This is what scale up computing is all about. Scale up computing is building heavy computers. It's super heavy, and you've got to be super strong to hold it. It's like Iron Man right there. Okay? And so this right here is probably, I'm going to guess, 300-400 pounds. All right? So this is 1 petaflops. 1 petaflops. 1 petaflops. 8 terabytes per second. 8 terabytes per second of memory bandwidth. Concurrent memory bandwidth. Every single GPU can communicate with every single GPU. Every single GPU can see each other's memory as of their own. And so this motherboard here with 8 volts goes into this computer, and there are 2 of them, which turns it into a 2 petaflops computer with 512 gigabytes of memory that is completely visible to all of the processors. Ouch. Okay? And so this is the ultimate example of scale up. And by putting all of this memory, all of this data into a DGX-2, lickety split, whatever you want to do. It's like doing data analytics like a video game, except it's several hundred gigabytes of data. And so instead of 2 hours on 20 nodes, or I guess half an hour on 50 nodes, and notice it's starting to slow down the scalability because the overhead of communicating between nodes using Spark is starting to overcome the benefits of having more nodes. And so 100 nodes is still about half an hour. And then when you do machine learning, classically iterative algorithm, where you would really like to have all the data on one node, notice that the scaling is just inconsequential. And so running XGBoost on this several hundred gigabytes of data, we're able to wrangle the data, engineer the features, and train the model in just a few minutes instead of 3 hours. That's incredible speed up. What do you guys think? Now, none of this stuff is possible if it wasn't because of Rapids, and none of it would have been possible if it wasn't because of Aero, and none of it would have been possible if it wasn't because of Dask. So I want to congratulate everybody that worked on it. None of it would have been possible if it wasn't because of Pandas, and none of it would have been possible if it wasn't because of XGBoost and Scikit-learn. All of this is exactly that workflow that you know very well. And now, for the very first time, it's accelerated completely like high-performance computing. And so this is a classic example of the benefits of scale up. And so this is what a data center looks like when you scale it out. And so you put a whole bunch of servers, and each one of them are commodity servers, and you have this software on top of it called the Spark Compute Engine, and turns this data center into essentially a microprocessor. That's the genius of the work that Mate did. Mate is absolutely a genius, and he turned basically a data center into one gigantic CPU. And you could write programs and unleash it on top of the data center, and it does its best to distribute the workload, and it ensures fault tolerance and resilience. Now, this is what it looks like if you scale up. And this is the power of supercomputing. This is what supercomputing is all about, and this is what supercomputing centers do, and this is what has inspired all of our work, working with all of you in the fundamentals of advancing scientific computing. This is what you get. One node. One gigantic node. And so as you guys know, people say supercomputers are expensive. But that's not true. This is expensive. This is a supercomputer. And the more supercomputers you guys buy, the more you save. That's right. Now, the truth of the matter is, this math, this economics, this analysis, you know very well. If it wasn't because of the scale-up machines that we make together, and you were to scale it out using commodity servers, the amount of power that it would consume, the amount of space it would consume, the cost it would consume is easily many times that of building a scale-up computer. So having this computer is fantastic, but you need software stacks. And I just demonstrated one software stack. This is our newest software stack, our machine learning and our data analytics software stack. There are millions of researchers around the world and data scientists around the world that's going to benefit from this, and that's the reason why there are so many partners that are taking it to market. Each one of these software stacks, and there are so many of them now, are optimized and they're tuned and they're maintained meticulously. But there's so many layers, so many libraries. What are the odds? What are the odds that a high-performance computing center can possibly find them all? There are so many different stacks. Hundreds of applications in a data center, 1,000 applications in a data center, a couple hundred applications in a data center at one time. And now as we move into the world of machine learning and deep learning, the number of models is going to explode. So the stacks are just really staggering. And so we've containerized all the stacks. Every single stack we optimize for, we run in our company's data center. We run, we test, we continuously refine, just as I showed you, and that's one of the reasons why I can demonstrate to you every single few months the performance of our stack continues to improve. We have a few hundred computational mathematicians and performance engineers working day and night on all of these different stacks to continue to improve its performance. And when we're done, we test it and then we containerize it. And we containerized it into several different segments: science, molecular dynamics, quantum physics, astrophysics, fluid simulations, grid simulations, finite element analysis, a whole bunch of scientific computing codes. Data analytics, there are going to be more and more of these things. So initially, QDF, the ingestion of data, the transferring of data, the processing of data, deep learning, you know very well, all of the different types of frameworks that are out there for one GPU, for all of our GPUs, for many GPUs in one node, and now for many GPUs and many nodes. That software was just checked into our cloud container store. Machine learning, I just talked about, all of the rapids, acceleration stacks. You can find the Python, the Jupyter notebook for the example that I just showed you. It's right up there in the cloud, and you just have to download it, pull it, and you can run it. And the beautiful thing is, data sciences has a lot of similarities independent of where you're in finance or retail or insurance, in marketing. The algorithms are relatively similar. The approach for engineering features are relatively similar. So you can download our example and modify that Jupyter network and apply it to yourself. And now it's fully accelerated. Hyperscale inference, super important thing to do. And the reason for that is this. A large hyperscale data center is a computer. And that's a resource whose cost is number one most affected by utility. If it's sitting idle, it doesn't matter how cheap the equipment is. The overhead will drown out the cost by itself. And so it is vital that utility is high. However, the workload that comes into a data center with 1 million servers in it is completely unpredictable. And it changes from time to time. It changes from season to season. And it changes from certain events in the marketplace. And so as a result, that data center has to be as agile as possible. The ultimate hyperscale virtualization is built on top of Kubernetes to orchestrate the entire data center. There are so many different types of workloads, as you could see, that are coming in these containers. It's just impossible to figure out how many of this and how many of that to build. And so it is incredible, it is important that vital that they create an infrastructure that allows them to utilize every single node as flexible as possible, of course, as high throughput as possible, but to be able to run different workloads at the same time. Our hyperscale inference server, and then rendering and visualization. When you do data analytics, there is just no replacement for looking at the data and looking at the analytics. And so I'll show you that in just a second. And so these are the stacks that we have, the categories, and they're all located in NGC. ngc.nvidia.com. Super easy to find. There's a whole bunch of new stuff if you haven't had a chance to check it out. There are new acceleration containers, machine learning, data analytics. I was just told that MATLAB is up there now. Super exciting. Multi-node acceleration stacks, not only multi-GPU, but multi-node. Singularity for all the supercomputing users. What do you guys think about Singularity support? So we have Docker for hyperscale, and now we have Singularity for all the supercomputing centers. Super excited about that. And we now have a program called NGC Ready, so that you know which computers are tested, which computers will run with the containers that are downloaded. And currently it looks a little bit different, but shortly it'll be organized like this. There'll be all these tabs on top, and then there'll be all these different applications you could download, and every one of these supercomputing stacks, this is like the app store of applications that you need for your life. This is not the app store for apps you want. This is the apps for apps you need. Okay? And so each one of these stacks are lovingly and expertly crafted, and they're maintained and tested and optimized. And so this is really one of the most important things of our platform, because we know that every single GPU is CUDA. Because we know that CUDA is in every single data center, and we know that every one of our architectures is in every cloud. And we know that every single one of our architectures and every single one of our GPUs has been maintained and tested and qualified to run all of these different stacks. Now you benefit by just going up to the cloud and pulling down one of these. And then you just grip it and rip it. And so all of these demos, they're not like a video game, and so they're hard to demo. But I thought that we would demo something anyways. Now we'll pull down one of the visualization stacks, and this is ParaView. What this is taking a supercomputer. We're going to download this ParaView container, and inside the ParaView container has, of course, CUDA and RTX, and one of the things that it has is this thing, and it's optics, and one of this thing has is called index. It has the ability to take a gigantic visualization database. For example, if you want to visualize seismic processing, if you want to visualize a supernova, if you want to visualize something so gigantic, there's no way to fit it in system memory. And you've got to distribute it across a supercomputer. If you want to visualize something that big, you'll pull down the ParaView container with our index SDK, which has all the software in it. It's all fully optimized. You pull that into your supercomputer, and let's show it to them. Peter, is that you?
It's Mark.
Okay, hey, Mark.
Hi. Okay, thank you very much.
So Mark, here, let me set you up and you go, okay?
Yeah.
All right, so here's what we're going to do. I know that most of you have never been to another galaxy. I just wanted to double check, okay? And so for those of you who have never been to another galaxy, we're going to bring it to you. This galaxy, turns out, is a dwarf galaxy. This dwarf galaxy is like 1/5 the size of the Milky Way. And it has hundreds of supernovas inside. Okay? Now, I've never been that close to a supernova, so you guys got to be a little careful here. We're going to be super close to a supernova. And what we want to see, apparently what happens, is that it just spews out enormous amounts of gas out into the universe. And new galaxies are formed. And so this is M82, right, Mark? This is M82. And we're going to see this new galaxy, this dwarf galaxy, just spewing beauty and gases out into the universe as new galaxies are formed. Okay, go ahead.
All right, thank you very much. To start our GPU accelerated multi-node containers, we first have to load Singularity. As you can see here, we first simply check what kind of GPUs we have. We have Volta's GPUs here. It's a DGX system, multiple DGX systems. And then we run a job on, right now, only 2 machines, 2 DGX systems.
This is a demo only this audience could love. This is being broadcasted all over the world. Mark, this is being streamed all over the world.
Awesome.
Yeah.
All right, and
people all over the world going to watch you type. Only this audience goes, yeah, I love that. So simple. They made it so simple.
We are using MPI and Singularity to actually run the NVIDIA Docker container that we pull from our repository. It's a ParaView server that we are going to launch on 2 machines with the NVIDIA Index plugin here. And what you're seeing now is how the Docker container is pulled, then extracted, and launched in a second.
Guys, I have to confess, we didn't rehearse, and so I have no idea how long this is going to take. And so Mark,
we are already
give me a
there.
hint.
We are there already.
Okay,
so
all right. The galaxy is huge. I mean, this M82 is big.
We are starting small. So we have our ParaView client already running here. We connect to the ParaView server.
Now, you told me earlier that it's like 70 terabytes.
7
okay?
terabytes are good.
Is it 700 or 70?
It's 7 terabytes.
Oh, 7
Very
terabytes.
soon.
Oh, so it's tiny. This galaxy is small.
It's just tiny, yes.
Okay, so we're basically we're going to render this is simulated, right? This is being simulated on a supercomputer, and it spews out 7 terabytes of data. Now, 7 terabytes will not fit in a computer, in a workstation or a computer. You can't render it. And so we take the 7 terabytes, we break it up into this new data structure, rendering hierarchical distributed rendering system we created called Index. Index is going to take this dwarf galaxy, it's going to render it in small pieces, and then Index is going to assemble, compose it, and present it to you for your enjoyment. Am I right, Mark?
Absolutely.
Okay.
What we're seeing here in a couple of seconds is the galaxy, but this is only one time step that we currently run on just these 2 nodes. It's a live demo. That's actually working. And Here we are. So this is the data that you currently see rendered on 2 machines.
It turns out we have an astrophysicist working at NVIDIA, all right? And so hey, Dr. Jones? Dr. Jones?
Hi, John.
Hey, these are the supernovas in the middle, right?
Yeah, that's right.
And it's spewing out in these 2 directions, but not in this disk way, in this disk format. Why doesn't it do that? Why doesn't it come out in a spherical way?
So the gas being spewed out actually goes in all directions, but it gets captured by the galaxy when it spews out sideways. But when it spews up and down with respect to the galaxy disk, then it just gets ejected.
Oh, that makes so much sense. And the reason for that is because the galaxy is spinning in a particular direction.
Yep, that's right.
I see, okay. See, this is the type of stuff we get to talk about at NVIDIA. We have, earlier on, you guys, there's Kate Clark, I don't know if she's in the audience, a quantum chemist. We have an astrophysicist. We have a couple of video gamers.
And now we want to go large. So what you have seen here is exactly what you can do also not only with 10 machines, 20 machines, you can do that with 27 machines or even more. But we have prepared a 7 terabyte demo right now for you to display it interactively.
Whoa, it's hot out here.
And so, this is now 7 terabyte in motion. And the scientists that created those are eager to really inspect the data interactively. They can change color maps, they can change the transfer function, they can zoom in to spots they want to investigate to really get insight into their simulation. It's a time-lapsed visualization here.
And so, Mark, it's important that the audience realize this is not 7 terabytes of video that's being played back. That's easy.
Exactly.
This is 7 terabytes of visualization data that we're visualizing interactively. That's why you can go in and out. And that's why you could interact with it and notice that, good God, there's something odd over there. Is that right? I just found something. I'll report it right after the show. Okay, so this is the M22. This is a dwarf galaxy. It has a lot of supernovas inside, and this is what happens when they're spinning around, spewing gas, exploding, I guess. And it looks really hot. Okay? Thank you very much, Mark. Good job.
Thank you.
Now, ladies and gentlemen, that is absolutely the best container demo you have ever seen. It is not possible to give a good container demo. Tupperware couldn't have done that. This is good container stuff. We're going to be known for jacking up containers. Dockers, Singularity, containers. Nice and simple, download it, grip it, and rip it. Okay? So we have a whole bunch of them. This is the body of work of practically our whole company. This is the body of work of the entire ecosystem. All of the scientists around the world working together for the last 10 years made this possible. We're looking at this registry and the amount of computer science that has gone in to make this possible, to refactor every single stack, to create new algorithms, to explore new worlds. Oh, come on, that was so good. These are this is container marketing at its best. Okay, all right, so this is I'm so proud of this, you guys. And this is, I hope all of you enjoy it. And then for people who want to know how fast their computers are, you don't have to look at a spec sheet that says this computer is this many gigaflops or teraflops or giga whatevers, how many pounds. You don't, after all of this computer science, we don't measure computers by its weight, nor should we should measure computers by its teraflops and megabits and terabits and gigabytes. That's so yesterday. We now made it possible for you to download applications and just measure it. Okay, so you guys could decide how best to architect computers and build computers. All right, so containers. NGC is our registry. It is not a cloud computing platform. The cloud computing platform is Google Cloud, is Azure, it's Amazon, it's so on and so forth. But this is a registry of containers, and you simply pull it down into the cloud, or you pull it down into your server, or you pull it down to your workstation. And today we're announcing, and they're just so excited about it, I'm so excited about it as well, that all of these computer makers and workstations makers and cloud service providers today are taking NGC-ready computers out to the world. Okay, thank you. So before I go into some new stuff, the new HPC market, which started out with scientific computing, with some early internet companies playing with distributed computing and hyperscale, which then opened up the whole open source, started with Hadoop and MapReduce, and then the Berkeley work, Berkeley Amp Lab with Mate Zaharia, with Spark, and then Wes McKinney and Python and NumPy from Travis Oliphant, and I mean all of their contribution, and Anaconda and Dask and Arrow contribution from the work that we did with the Go AI startups and Wes McKinney, and boom, 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 all of that turned HPC, what I just showed you, into a high-performance computing market. This new way of doing science called data science is now accelerated because Moore's law has come to an end and distributed computing doesn't scale. It is now accelerated by rapids. All of this code is put into NGC, the NVIDIA GPU cloud. It's optimized, it's containerized, it runs on Docker, it runs on Singularity, it runs on Kubernetes, it runs on bare metal Linux. It's taken out to the world from all of the partners, server makers, workstation makers, cloud providers. This entire acceleration stack is now ready for you to enjoy. The future of HPC, which started out with scientific computing, supercomputing labs, are going to be transformed. We are going to welcome large industries, retail, finance, energy, insurance, healthcare, transportation, logistics, all industries with gigantic amounts of data that currently either the data scientists can't get to it because Pandas doesn't have the ability to process that much information, or Spark is too difficult to use for early science, data science work, and it's not fast enough for most of the data sizes that we're dealing with now. Now the industries will come. All of the internet service providers surely are moving to machine learning. What started out with just a couple of companies, Google and Yahoo, is now everybody. You can't have a mobility as a service happen without machine learning. You can't deliver food from a restaurant to your home without connecting a three-sided platform, customers, restaurants, and drivers, without machine learning optimization. All of these companies are clamoring at figuring out ways to accelerate their machine learning and their data science. And then a new phenomenon is coming. The world is going to get connected by sensors. And these sensors are going to be streaming in raw data. And we can't afford to save it, think about it, process it, and do something about it. You're just going to have to do machine learning in real time. And there's just no way to do it if it's not accelerated. We believe that the future of HPC is going to get redefined basically the entire computer industry will become HPC. Because the killer app is data science. The killer app is machine learning. Some industries will do more deep learning than machine learning. This is all machine learning right here. Very little machine learning here. High-performance computing will have a lot of machine learning because biology and healthcare and most of those industries still benefit from machine learning, and it is the best way to get at it. Some of them will use deep learning. Most of the internet companies would have transitioned from machine learning to deep learning by the time 2025 comes along. And most of the industry, most of the enterprise, will probably be on machine learning, with the exception of a few. So what that basically says is this. The future of high-performance computing has 4 characteristics. The first characteristic is that Moore's laws come to an end. You got to find a way to accelerate it. The second, you can't just focus on one application. The reason why the CPU has remained so popular, despite the fact that Moore's law ended practically 8-10 years ago, is because of its utility. The utility of a microprocessor was so high that accelerating just 1 or 2 or 10% of the application doesn't tip the needle. But finally it has. Finally it has. We now accelerate the vast majority of the science workloads that are in data centers. Deep learning is all completely accelerated, and machine learning, as you can see, is now accelerated. The diversity of workloads in data center is great. And then lastly, there are 2 architectures. And we have to work towards both of those architectures advancing. There are workloads where only scale up is possible because the overhead of communicating between commodity clusters are too high. And the second is we also have to solve the scale up problem, the scale out problem. So scale out is supercomputing, scale out is hyperscale. Scaling out, if you look at this pie, the vast majority of the computers in this pie will be scale-out computers. And the reason for that is because they'll be sitting in clouds. And the utility, the fungibility of a scale-out computer is greater than a scale-up computer. It is easier to fractionalize. It is easier to fractionalize a scale-out computer so that you could serve more customers. But we still have to find a way to speed it up. Scale-up and scale-out looks like this. The ultimate example of scale-up is DGX-2 there for a personal supercomputer and a supercomputer for the world, the Summit. This is about making bigger and bigger physical machines. One node, bigger and bigger and bigger. One operating system, one image, bigger and bigger and bigger. You're pushing against the laws of physics every day. You're pushing against the laws of everything every day. This is hard stuff. On the other hand, hyperscale. Hyperscale is easy to conceptualize on a computer level. A whole bunch of commodities being all connected together, but it is a gigantic software problem. And that's the reason why Hadoop was such a groundbreaking piece of work, why MapReduce was such a great groundbreaking piece of work, why Spark is such a groundbreaking piece of work, why Kubernetes is going to change everything, why Docker is so important. All of that is because hyperscale, managing this incredibly dynamic and volatile workload, is so difficult to do. Scale up versus scale out. Our scale up strategy is simple. You saw it. Our scale up strategy is right here with DGX-2. And it's really about continuing to advance the processor and making more and more of them being able to communicate with each other. And I just got to say, as I look down on this computer, if you look at it from my vantage points, those are all knives. You see those? I just noticed, I'm just grabbing this thing, there's like 45 knives coming my way. Ow! Notice nobody ran to the stage. Nobody said, "Are you okay?" Supercomputing is hard work. And so we took a microprocessor which is having a hard time scaling up, and we connected it to a ton of flops. But those flops are connected to a ton of bandwidth, to a ton of memory. But the challenge is, how do we get it to see each other so that the aggregate computing memory space is large. And so we created this thing called NVSwitch. And as a result, we now have 2 petabytes, 512 gigabytes of data accessed at 16 terabytes per second. It is an utterly shocking number. And it's the reason why what would have taken 3 hours on a cluster of tens or hundreds of servers became a few minutes. This is scale up. If you want to visualize what scale up looks like, this is what DGX-2 is doing. And here we're training a deep learning model. And this particular deep learning model is called Transformer. And Transformer with multiple something of experts. Do you guys, multiple what of experts? What? Mixture of experts. Okay. So thanks. Appreciate that. And so mixture of experts. And basically it's an ensemble network that allows us to do a really good job with language modeling. And so if you were to train this network on one GPU versus a whole bunch of them connected on separate servers, notice over time, the overhead of communications starts to get in the way of computation. And so the more servers you buy, the slower it gets. It's a weird phenomenon. Otherwise known as large organizations. People spend too much time talking to each other. Nobody's doing any work. Okay, so you got to keep things small. Or you have to really enhance your communications bandwidth, which is what we do. All right, so here's a V100, it's 16 of them, and it's practically linear. This curve right here is the power of scale up. Does that make sense? All right, so scale up. Well, there's some applications where, unfortunately, you can't distribute. It's a classic scale-up problem. We're going to simulate the weather. Now, we're going to simulate the weather. This is just an extraordinary thing. We're going to simulate the weather at 1 kilometer resolution. We're going to simulate micro-weather. If you don't simulate at 1 kilometer resolution, you lose all of the impact of elevation because, mountain ranges, 1 kilometer, hills and valleys are completely lost if your resolution is 10 kilometers, and cloud cover is completely impossible to simulate. Microclimates requires to reduce the simulation resolution to 1 kilometer or so. This is going to be your first super real-time, 1 kilometer weather simulation in one box. It's going to replace 75 servers in one box, and it has to be super real time because that's one of the criteria for predicting the future. Okay? So you have to be a time traveler so that you could predict the future. And so I think, Peter, you're going to show me this demo, yeah?
Yep.
Okay, Peter.
All right. So what we're seeing here is a large chunk of Central Europe. It's an area of about 1 million square kilometers that's currently modeled with the Cosmo weather forecast code. It's fully GPU accelerated, and as Jensen said, it's running on a single DGX-1. It covers about 2 days of forecast in about 20 minutes. And what we're seeing are clouds in the northern part of the Alpine region. We see the isolines of pressure, and we see the wind with these little streamlets. Now, so you wonder, why do you want to visualize it in such a high-quality form? Well, on one hand, there's the educational and outreach purposes, but there's also the idea that you can actually start to investigate the 3D structure of clouds. One thing that if you're just dumping every once in a while a data set and you're just looking at it occasionally, you're losing a lot of the dynamics, and with being able to directly look into the data as it's being produced, gives you much more insight, and you can actually look at more data than you would be able to save to disk.
This is just really kind of amazing. I mean, guys, we're not looking at a video right now. We're looking at a future prediction of microclimates. Now, making this simulation go faster is not about just making the simulation go faster. What's really amazing about this is now we could apply this weather prediction, micro weather prediction, or regional weather prediction for economic reasons, for transport reasons. You got ships coming in. You want to make sure that they're safe, that Wednesday is a good day to pull them in. All of a sudden, logistics change. The application for microclimate simulations is far, far, far more than just helping you decide whether you got to wear a sweater to Dallas or not, which, by the way, the answer is yes. My gosh, I've never been so cold. Peter, that's a great demonstration. I really appreciate that. Good job. Okay, so DGX-2 was such a groundbreaking piece of work. It's the first computer in the world that's 2 petaflops, sits in a box. But the most important thing is 512 gigabytes of data, all completely accessible to every single machine. We created a box and all of the software on top of it, as you can see, of course. But what's most important, what I keep holding up, is the HGX-2 motherboard. And OEMs and servers, computer makers all over the world are building HGX-2 high-performance computing servers as we speak. But the moment that DGX-2 became available, people just came and ripped it out of our hands. And it's in national laboratories around the world. I'm so excited about this. So this is scale up. Okay, so for those in the supercomputing industry, you know this very well. This is scale up. Now I want to talk about scale out. You want to scale up a computer, and that's very clear. That's very clear. However, that computer is really designed for few people, gigantic jobs. Few people, gigantic jobs. The rest of the world is about enormous number of people, enormous number of jobs. And those number of jobs, those jobs are milliseconds each, not days each. You're not simulating a job for a week or a month. You're simulating a job for a few hundred milliseconds. You want to get in, get out, and it's going to make a prediction about something for you. And so we believe that the future is about scaling up using acceleration, NVLink, tensor core, artificial intelligence, multi-precision, accelerated stacks, put them in NGC, make it available everywhere. That's our first strategy. It's called scale up. And every single year I've come to supercomputing, you've heard me really basically only talk about scale up. Scale up, scale up, scale up, scale up, scale up. This is what enabled deep learning. This is what enabled supercomputing. This is what made it possible for us to democratize supercomputing with a small version of this, a little graphics card, that researchers all over the world are using. We now want to talk about scale out. But before you scale out, the first thing you should do is just scale up and then scale out. Because scale out has limits, as you saw. The curve that I showed you of transformer training is no different than machine learning running XGBoost or random forest or somebody doing machine learning on a data center of commodity servers. And notice, in the machine learning example I showed you, the curve actually looked exactly the same. Between 50 and 100 servers, the performance didn't change that much. And so it was starting to peter out because the communications overhead was overwhelming the computational part of the processing. So the first thing we think we should do is scale up. But however, if you look at this data center, the servers inside are tiny. There are a million servers in this thing, and it's tiny. These are tiny little, super, super dense, super small computers. Here's one. Hang on a second. I feel like I'm risking myself every time I do this. All right, so this is half of a node. That's 8 nodes. And so you can just imagine the difference between this architecture and this architecture. This is called the Hyperscale architecture. This is scale up, supercomputing architecture, high performance computing. And this is going to be the future of high performance computing as well. Today, it's called Hyperscale. But we're going to change all that because in this magical tray, are two of the world's most advanced GPUs that we just announced. Ladies and gentlemen, I did it on purpose. Two NVIDIA T4 cloud GPUs. I didn't have to do that. I've been carrying one all along. And so guys, here it is. This little candy bar here is one of the world's most advanced processors. I'm going to tell you about it in just a second. It is crazy, crazy fast. Little candy bar here. Easy to carry around. You know, for anybody who's a tech geek, you know, if you want to impress somebody, all the guys always have one around. Hey, let me tell you what I do. Your phone wouldn't work without this. And it goes into this, goes into an OCP server. It's industry standard. And it's really hot pluggable. And so, there you go, okay? And so that's how Hyperscale works. What you just saw is the brand new NVIDIA T4 cloud GPU. Now, this little tiny bar here is Pascal. Now, if you purchased a Pascal, don't feel bad. There's something much, much better, though. It's called a T4. This is 70 watts, 65 teraflops of tensor core, 65 teraflops of tensor core. And you guys saw earlier, using the Magma iterative refinement solver, you're able to achieve FP64 with tensor core FP1632. And that's 65 teraflops. So imagine just some ratio, some percentage, like say a quarter of that would be FP64. It's incredible. Int8, 130 teraops. And because everything is multi-precision and you can mix and match, some of the layers could be Int4, some of the layers can be Int8, and the accumulation is 32-bit. This is not Int8, this is Int8 tensor core, this is Int4 tensor core. The combined fusion of all that multi-precision gives you the benefit of accuracy and incredibly high throughput. And all of that in this little tiny candy bar we call the T4 Cloud GPU, and its maximum power is 70 watts, lower than a CPU, a couple of orders of magnitude more performance. We'll test out my claims in just a second. And combined with our TensorRT 5.0, which was just released that supports Tensor Core, the performance is out of the world. And it also achieves the lowest latency, the absolute lowest latency. People have always thought that GPUs are fantastic at high throughput, but we've clocked in the lowest latency, less than a millisecond, of GoogleNet. You could go build a custom ASIC and you won't beat that. The lowest latency of any network we have ever seen, 1 millisecond for ResNet 50. Incredible performance. But that's just the beginning. Building this processor, this Turing GPU that is designed for AI, was really the life's work of a lot of people at NVIDIA. The rest of the people at NVIDIA were building the software. The software stack that goes with this is just extraordinary. This is where Kubernetes comes. This is where all the multi-model, multi-framework, our NVIDIA Docker, the CUDA SDK, cuDNN, TensorRT 1, 2, 3, 4, 5, and then this brand new piece of software called the TensorRT Inference Server that allows multiple models to run concurrently on one server and to be able to work with Kubernetes to load balance everything. And it just makes it so easy for you to go to NGC, download a container, into one of the clouds and do magic, And so I think we ought to do that. Speaking of magic, ladies and gentlemen, every year, Ryan Olson comes along with me, and he does magic. Now, his magic trick, as you know, is based on this incredible demo we call flowers. Okay? Last year, you guys saw flowers, right? So should we switch over to flowers? I want to show you flowers like you've never seen flowers. So first of all, flowers. All right? Now Ryan and I promised each other that we would learn one flower each conference. Oh, I found it.
There it is.
Right there. I found it first. You owe me $1,000. Okay, so that this is what you do in the middle of the night. Okay, so we both, I know what that is. What is that? Tiger lily. That's right, tiger lily, ladies and gentlemen. It's a lily, but it's yellow and has spots. Figure that. Okay, tiger lily. And so this is a miracle right here for all of you who aren't spending a lot of time thinking about deep learning. This is a miracle. This is a deep learning framework called TensorFlow. The container has been pulled down into Google Cloud, and the CPU is currently inferencing. The fastest CPU instance there is inferencing, classifying these flowers at 4 images per second. So literally, all you have to do is create an instance in the cloud. You could be on the phone, you could be on a browser, a PC, doesn't matter. You create an instance in the cloud. You download the software called TensorFlow, and then you send it a bunch of images, and it classifies it for you. It says tiger lily, okay? And it does it at 5 frames per second. Here's the problem. There's so many people using the cloud. 5 frames per second, 5 images per second is simply too slow. And so what Ryan wants to do is he said, hey, guess what? Wouldn't it be amazing if Google Cloud has adopted the NVIDIA T4 and deployed it into their Google Cloud in less than 30 days after we went to production? That's what he said to me. He said, wouldn't it be amazing if, I said, well, funny you should say that. Because I think we ought to go to Google Cloud and find out how many they already have started. And so here's what Ryan has to do. So this is Ryan's journey. First of all, he has to go to Google Cloud. So he goes to the Google Cloud. And in the Google Cloud, whoa, I'm standing in front of Google Cloud. All right, so here's in front of the Google Cloud. He has to go there's an instance somewhere, right? So he creates an instance. You see that? Okay, creates an instance. And you could either use CPUs, but suppose I wanted something different. Suppose I wanted an amazing NVIDIA Tesla T4. Oh, here you go. So here's the NVIDIA T4 right there in Google Cloud. This is available right now. NVIDIA Tesla T4. So now you've created this instance. This is a machine, a bare metal machine. You need some software for it, right? And here's the beautiful thing, Ryan. You're just going to go to NGC, also in the cloud. And NGC brings you here to the front page, and you got to decide what you want to do. And you're saying to yourself, you know what? I want to create a business to classify flowers. Okay? And I just raised $10 million. I'm going to classify flowers, and I'm going to classify faster than anybody. I'm going to have so many customers, right? And so you come in here, and you go to one of our containers, the inference container, and you need a container that has Kubernetes because you're expecting to have a lot of customers. Are you not, Ryan?
Tons.
Right? You're tons of customers. You're expecting to go from 0 to IPO overnight. And so you need Kubernetes, and you need all of the world's best software, and you need it all containerized. And so you come over here and, TensorRT inference server.
Yep.
You pull that sucker down. You see that? Okay? Nice and easy like that. You do some typing.
There.
You and Mark
Copy and paste
both. Some of our best typing people. And so you do some typing, and then you go back to Google Cloud, right? You don't have to do much typing. You go back to Google Cloud. Now you have an instance. You've downloaded software on top of it, and so what you have is a virtual machine. Okay, so you now go to the virtual machine, and this virtual machine, there's a virtual machine created that experts, has dedicated his whole life, expert at classifying flowers. Okay, and so
Should Should we see it?
Yeah.
All right.
And so now you've created this machine, and it's expert at classifying flowers, and so, boom, he starts it up. Okay, so here comes the good news. The good news is that you're classifying flowers at superhuman levels, and nobody even understands how this is happening, right?
Oh, yeah.
Right? Normal humans are going around taking pictures of flowers like, what? That's a tiger lily. He's right. Okay? And so people are so amazed at this. People are taking pictures of flowers all over the world, and as it turns out, they're overwhelming your data center. Are they not? They're overwhelming your data center. You know that commercial where you look and you go, you got 0 customers, and all of a sudden you go to 1 million customers and you start sweating. And so
Yeah, this is what happened.
the good news is, oh my goodness gracious. So all these customers are coming in, but guess what? You got Kubernetes. You've got NVIDIA T4 with the Kubernetes TRT inference server running on the Google Cloud, and they got as many T4s as you want, right? And so the number of customers keeps coming in.
Yep, so no problem. I got more customers. I just crank it up. You want to see how fast we can go? This is probably not a Gordon Bell Prize, but we're getting close.
That's a lot of flowers. Okay, so billions of dollars of R&D later, flowers. Everybody in the ecosystem. You know, gosh, all of the people that work so hard inventing all of this stuff, and now supercomputers in the cloud, ladies and gentlemen, flowers. It's just incredible, incredible. So, good job, Ryan. Beautiful flowers. So let me do some math. What I think I saw was 6,600 images per second versus 5. Am I right? 6,600 versus 5 on a CPU. Almost 1,500 times. Not bad for a candy bar. Ladies and gentlemen, the world's most powerful candy bar. There are over 50 server designs in the world happening right now. Every single computer maker in the world has signed on and are building T4 servers. And I'm just blown away at how fast the Google Cloud team works. Diane Green and the team work so incredibly fast. From the moment that this thing came out of the production line, less than 30 days, it was deployed at scale in the Google Cloud. There must have been a Google employee once there. Incredible. Incredible. This is only possible because the entire software stack is compatible and ready. You want to run whatever you want to run, it just runs. You want to run whatever you want to run, it just runs. All the models, super fast, Kubernetes. They could run it in one data center. They could run it across multiple data centers. You could run it from a data center all the way to prem. One single platform. It's completely invisible. Ryan could have shown it to you, but he could run some of it in our data center, Saturn V, where we're testing this. And so some of the workload is running on Saturn V, some of the workload is running on the Google Cloud. And it's completely seamless. Nobody even knows. It's just incredible, incredible. So this is the NVIDIA T4 Cloud GPU. So that's it. That's it. This is what I want to talk to you about. The HPC industry is fundamentally changing. It started out in scientific computing, and the architecture is largely scale-up. And its purpose in life was to simulate from first principle laws of physics, Maxwell's equations, Schrodinger's equations, Einstein's equations, Newton's equations, to simulate these equations from first principles to derive knowledge, to predict outcomes. Well, the future is going to continue to do that, but we have a new tool, and this new tool is called machine learning. Well, machine learning has two different ways of approaching it. One of them, it requires domain experts to engineer the features. Another one, using convolutional neural network layers at its lowest level, learning what the essential features are, the critical features are by itself. Each one of them have their limitations, and each one of them have their applications, and both of them will be incredibly successful. The future high-performance computing architecture will continue to benefit from scale up, but it will be scaled out as the IBM Summit supercomputer that we worked on together. Each node is powerful like that HGX-2, but there's a whole bunch of those nodes. Scale up and scale out. That gives you a supercomputer. On the other hand, a T4 added to that little OCP server is a scale up. And then you scale it out. In the future, architecture will be scale up and out, whether it's high-performance computing or supercomputing. We have a scale-up architecture we called the HGX. And we recently launched into production the Turing architecture, which is our first scale-out accelerator for our scale-out cloud data center strategy. It's available on GCP now. But none of this is useful unless we have software. Accelerated computing is not about the chip. Accelerated computing is something that I dropped a phrase in a decade ago. It used to be called application acceleration. I dropped the application part because I thought it was just cumbersome. But it doesn't change what you're ultimately trying to do. You're ultimately trying to think about the application first, about the researcher first, about the developer first, and to create an entire stack that allows us to overcome what otherwise would be called the end of Moore's law. Accelerated computing is about accelerating stacks. When you accelerate stacks and you don't have a coherent architecture, I have no idea how people are going to use it. The one great decision we made a decade ago is called CUDA everywhere. We made the decision to make every single GPU, whether it's used for embedded systems, for medical imaging, to gamers, goes into cars and robots, all the way to supercomputing centers, all retain the laws of a computer architecture, compatibility. And so we retain compatibility and the discipline of keeping it compatible. We're now on CUDA 10. As a result of that decision, we could have all of these stacks sitting up in the cloud, fully accelerated, fully optimized, and then now simplified in containers because of the great work done by Docker and Singularity, great invention. We can now download all kinds of different stacks. They can run them completely separately. Some of it could be running on CUDA 9, some of them could be running on CUDA 10, and all of these stacks are running in your data center, all of it in the NGC. And then lastly, we introduced a brand new stack that I'm so excited about. It is the work of a 10-year journey, started in early part of this decade through a lot of great work from a lot of great people. It made it possible for us to accelerate the two new HPC markets, the world's hyperscale, which will still have an enormous amount of machine learning, and the world's industries, which will be largely data sciences and machine learning for the next decade. This is the future of the HPC industry that we built together. And I want to thank all of you for coming today, and have a great Supercomputing 18.